given by Tom Morgan from Harvard.
Audible here? Okay, cool. All right, and we've gone forward a couple. Okay, thank you. So I'm Tom. I'm going to be talking about reconciling graphs and sets of sets, which are a pair of reconciliation problems. I'm going to start by describing what I mean by reconciliation problems and then talk about the background, which is, so we're auto-advancing again. The last time it wasn't with...
This is just PDF.
Yeah, it's PDF, so how's it advancing?
So it doesn't have the time.
I shouldn't think so.
Probably you can just do this
Okay.
and a pointer is
Yeah, I'll try not using the pointer. Okay, so I'm going to talk briefly about what I mean by reconciliation problems, then talk about set reconciliation, which is kind of the quintessential reconciliation problem from which derives the term reconciliation. Then I'm going to talk about our specific reconciliation problems that we introduce here and some protocols we develop for them. It's advancing automatically. I'm not sure why, because it's just a PDF. Okay, well, I'll just power through for now. I'm going to have to periodically back up as it automatically advances. Okay, so by reconciliation problems, I mean problems where Alice and Bob have some data and get a full screen? Okay. Okay, more likely to succeed here? Okay. Okay, so these are problems where Alice and Bob each have some data, and their data is close to each other in some problem-specific way. So Alice has A, Bob has B, they're close, and Bob wants to, they want to engage in a communication protocol so that Bob can recover A fully from Alice. Naively, one could just transmit A directly from Alice to Bob, but we'd like to exploit their closeness in order to do this more communication efficiently. And so we're going to be focused on this one-directional notion where just Bob recovers Alice's data. Some reconciliation problems are described more often where Alice and Bob both recover some combination of Alice and Bob's data, but if you can do the one-directional version, then Bob can compute whatever he wants offline, whatever combination of A and B offline, and then transmit the delta to Alice. And these kinds of problems have fairly natural applications to distributed systems, especially periodically synchronizing data between distributed systems. So the quintessential reconciliation problem is set reconciliation, where Alice and Bob have sets from some universe, and their sets are of size of most n, and the closeness of their sets is that the set difference is at most d. And we're going to assume that Alice and Bob have some bound on D. There's ways to address the case if you don't know D, but we're going to assume for this talk that we know D. And then, so the problem is to using as little communication and ideally computation as possible, we want Bob to recover Alice's set. So the naive solution, of course, is direct transmission of Alice's set, which would take order n log u bits. And there's an information theoretic lower bound of order d log u bits. Now, the state-of-the-art protocol for set reconciliation uses what's known as an invertible Bloom lookup table, because computer scientists are great at naming things. We're going to call it an IBLT. And so this is a kind of hash table where, like a Bloom filter, each key is hashed to more than one cell. But unlike a Bloom filter, where each key or each cell has only a single bit, here each cell has lots of information. It's got a count of the number of keys that have hashed that cell, a sum of all the keys that have hashed that cell, and there's an additional hash function we use as a checksum, where every key, we compute the checksum of it and compute the sum of all the checksums of keys hashed to a cell. And it supports a few operations. You can easily add and remove keys by updating the corresponding cell entries. If you have two IBLTs using the same hash functions, then they can be merged to represent the sum or difference of their items by adding or subtracting their cell-by-cell contents. But most importantly, if there are enough cells, we can extract all present cells in the table. And the way we do this is with a peeling procedure, where in this example, here we have an IBLT with only the count and key sum entries, and there's 4 keys that have been inserted into the table, 3, 5, 2, and 1, with the arrows indicating where they're hashed. So if we want to extract all of the keys from this table, we observe that the first cell has a count of 1, meaning only one key has been hashed there, meaning its key sum is exactly the value of the key that has been hashed there. So we can extract that key and then remove the key from the table, which exposes new count 1 cells, which allows us to repeat the process. This is a peeling procedure where we peel off the keys one at a time until we extract all of them. And through some random hypergraph analysis, it's known that this peeling procedure will succeed with high probability, requiring only a linear number of cells in the number of keys. An additional important feature of IBLTs is that the key removal operation is meaningful even if the key hasn't previously been added to the table. In particular, you can still perform that subtraction with a key that wasn't previously there, and what you'll end up with are what we'll think of as negative keys that are floating around in the table, and you can still peel these so long as you have an appropriate number of cells by identifying cells with counts of -1 and then peeling off the key and adding it back into the table. There's a nuance that this introduces, which now that we have positive and negative counts floating around, a plus or minus 1 count no longer uniquely identifies a single key, but this is where the checksum comes in. We compare the checksum of the key sum to the sum of the checksums, and if those match, then with high probability there's only one key there and we can peel. So now that we have the IBLT, how we use it for set reconciliation is Alice just makes an O of D cell IBLT, inserts all of her items as keys into it, sends it to Bob. Bob removes all of his set elements from the IBLT, and this will cancel out all the set elements they have in common, leaving only positive keys corresponding to Alice's set, negative keys corresponding to Bob's set, and there's at most D of these, so the peeling will succeed with high probability, and Bob can recover the set difference and then get Alice's set. And this only takes D log U communication because it's only O of D cell IBLT. Each cell takes log U bits, and IBLT operations are all constant time, so this is a linear time procedure. Okay, so now that we have IBLTs, we're going to use them with our new work, which is reconciling sets of sets. So this is a protocol we proposed where Alice and Bob, instead of having single sets, they each have a parent set of child sets. And the total number of child set elements adds up to n, and we'll have a bound on the number of set elements within a child set of h. And our closeness measure is now that the total number of child set updates, additions and removals from Alice and Bob's child sets suffice to make them match, make their two sets of sets agree. As before, we want to minimize communication, so Bob recovers Alice's set of sets. Another interpretation of this bound D is you can imagine taking the min-cost matching between Alice's child sets and Bob's child sets, where the cost of matching them is their set difference, then the total cost of this matching is D. Our protocols won't generate this exact min-cost matching, but it's a useful conceptual tool. So before we get into protocols, let's take a step back and wonder why might we study this problem. It might look a little arbitrary at first, but has a variety of more and less direct applications. The most straightforward application is to synchronizing binary databases. If Alice and Bob have binary databases of unlabeled rows and labeled columns, then and a small number of bit flips, almost d bit flips, suffice to transform Alice's database into Bob's, then this exactly corresponds to our set of sets problem, because unlabeled rows are equivalently a set of rows, and a row can be thought of as the set of columns it has a 1 in, and then flipping a bit exactly corresponds to adding or removing an element from that set. So it's the exact same problem. It can also be used as a subroutine in a lot of other reconciliation problems. For example, if Alice and Bob have databases of documents, a common way to represent documents for comparing similarity between them is what's known as shingling, which amounts to creating a set for each document where similar sets correspond to more similar documents. So you could use this to synchronize shingles as a first step into identifying more and less similar documents between the databases. We're going to talk a little later about our application to reconciling unlabeled graphs. And in a future work, we've got, we use it as a subroutine for robust set reconciliation, which is a geometric generalization of set reconciliation. Okay, with that in mind, our first attempt at solving reconciling sets of sets is to just pretend it's not a set of sets, just reduce directly to set reconciliation. This is, one step more involved than just naive direct transmission. And unfortunately, if we have bound h on the number of elements in the child set, the size of our universe of child sets is u to the h, so the total communication just directly reducing to set reconciliation is dh log u. In general, this is not going to be very good unless you have a really tight bound on h, so we'd like to do a little better. Now, for regular set reconciliation, recall that we solved it by interpreting sets as IBLTs. So perhaps for reconciling sets of sets, we can encode our sets of sets as IBLTs of IBLTs. And in fact, that's exactly what we're going to do. So Alice and Bob can encode each of their child sets with an O of D cell IBLT, and then Alice inserts all of these into an O of D cell parent IBLT, which she sends to Bob. Bob removes all of his O of D cell child IBLTs from the parent IBLT, recovering all of the child IBLTs corresponding to differing child sets. He can then try to recover Alice's differing child sets by just trying all combinations of these child IBLTs. He won't know, or she won't, Bob won't know which of Alice's child IBLTs will match with which of his. So he just tries all pairs, and one pair will work for each of Alice's child sets. So eventually, after all of these, he'll recover Alice's whole set of sets. And this takes d squared log u communication, because, d log u bits per child IBLT, d squared log u for the parent IBLT. But we can do a little better than this with our final protocol, where we use even more IBLTs of IBLTs. But the way we're going to do this is we're going to imagine first looking at our min-cost matching between Alice and Bob's child sets, and order the child sets by the cost of their matching, increasing order. And then we're going to imagine grouping the child sets into buckets, where the top bucket, the 0th bucket, are all the child sets they have in common. Then the first bucket are the child sets that have one difference, and then the next bucket has 2 or 3 differences, then 4 to 7, 8 to 15, so on and so forth, exponentially increasing the number of differences in the following buckets. And there's 2 useful properties about this bucketing. The first is that there's at most log d of these buckets. And the second is because the total number of differences adds up to d, the number of child sets that can exist within each of these buckets, although the number of differences grows exponentially, the number of child sets within them must shrink exponentially. And so we're going to use this to, instead of having one IBLT of IBLTs to recover the entire set of sets, we're going to have one IBLT of IBLTs for each of these buckets. And Bob's going to recover each of these buckets in series using a different IBLT of IBLTs. So in particular, we'll use log d IBLTs of IBLTs, where the ith parent IBLT has a number of cells that's exponentially decreasing, corresponding to the maximum number of child sets that can be in the ith bucket, and the ith child IBLTs have an exponentially increasing number of cells corresponding to the number of differences in the ith bucket. And so using this IBLT of IBLTs, Bob can immediately decode it, recover the child IBLTs, and then by trying all pairs, recover not all of Alice's differing child sets, but the ones that have at most one difference, thus the first bucket. and then by plugging what he recovered from the first IBLT of IBLTs into the second one, he can recover the second bucket, and just continue through naturally until he recovers Alice's whole set of sets. And so this takes d log u communication, improving over our previous result, and it's the best we know how to do. And the running time blows up a little bit, but it's still nearly linear. Okay, and that's all I want to talk about for a set of sets, and now I'll talk briefly about graph reconciliation, which is another new problem we propose, where Alice and Bob have unlabeled graphs, and our closeness measure is the number of edge additions and deletions it takes to transform Alice's graph into something isomorphic to Bob's graph. Note that if we were looking at labeled graphs instead of unlabeled graphs, this would be a very easy problem, because we could just apply set reconciliation to the set of labeled edges and we'd be done. But this still has applications to any situation where the two parties have graphical data that they want to synchronize, but they don't have agreed upon set of labeling for the vertices, for example, anonymized social networks or perhaps some maps. Now, when trying to solve this problem, the first thing you might think is this looks harder than graph isomorphism, or at least as hard as graph isomorphism, because determining if 0 edge additions or deletions suffice is exactly graph isomorphism. And we would like computationally efficient protocols, so I'm not going to try to tackle all of like fully general graph reconciliation and thus fully general graph isomorphism. So instead we'll look at specific classes of graphs where graph isomorphism is known to be easy, or there are tractable solutions, such as random graphs or structured graphs, like forests or planar graphs. So what I mean by graph reconciliation on random graphs, the model we're going to use is going to have an initial random graph, Erdős-Renyi GNP random graph, n vertices, each edge exists with probability p, and then basically we apply d adversarial edge updates to create Alice's graph and Bob's graph from that original graph. And per usual, we want Bob to recover a graph isomorphic to Alice's. Now, how we're going to solve this is we're going to use techniques from random graph isomorphism. The common strategy used in random graph isomorphism is to assign each vertex what we'll call an isomorphism invariant signature. So it's isomorphism invariant, so relabeling the vertices doesn't change the signature. And then the way these algorithms work is they argue that with high probability in your random graph, every single one of your vertex signatures is unique. There's no duplicate vertex signatures within the graph. And if you have such a signature scheme, then it's very easy to check if two graphs are isomorphic, because first, they must have the same set of signatures, and second, if they have the same set of signatures, then the isomorphism between the two graphs must match same signature vertex to same signature vertex, so you can then just compare labeled graphs. The simplest signature scheme, and the first that I'm aware of, was that of Babai et al., where they take, for a specific choice of H, the H highest degree vertices, their signature is just their degree, and the rest of their vertices have an adjacency vector, a bit vector of length H, indicating whether or not that vertex is adjacent to each of the H highest degree vertices. So for example, if H was 3 in this graph, this would be the signature scheme. The 3 vertices in the middle have degree 5, 4, and 3, and they're the highest, and then the rest are adjacency. And just as a quick example of why it's important to not just compare the signatures, in this graph, these two graphs have the same signatures, but they aren't isomorphic because it's missing the top right edge on the right graph. So how we're going to use the signature scheme back in graph reconciliation is we're going to use it to try to determine what we'll call a conforming labeling of Alice and Bob's vertices. So we'll say a labeling is conforming if the same vertex, if you think back through the original random graph that we generated and transform the graph into Alice and Bob's graphs, preserving which vertex is which, the same vertex will have the same label in the two graphs. And so what our protocol looks like using conforming labelings is first to use our signature scheme to, we'll interpret the signatures as sets and then reconcile them using sets of sets reconciliation. And then we argue that these signatures are sufficiently robust to our small number of edge changes that we can use them to recover a conforming labeling of the vertices. And then once we have a conforming labeling of the vertices, as we said at the beginning, labeled graph reconciliation is easy. Just use set reconciliation on the labeled edges. And I don't have time to get into exactly how we prove the robustness of these, but I can show you the results. Using Bidal's signature scheme, so the robustness gives us this trade-off between how many edge changes we can support versus how many edges there are in the graph, a trade-off between D and P that the protocol will work for. With the scheme of Bidal, we get a trade-off that uses, for constant number of edge changes, we can have P as small as n to the minus 1/7. For P as 1/2, we can get as many as n to the 1/9 edge changes with a very efficient protocol. And then we also looked at another scheme that gives us a somewhat less efficient protocol, but works for a much larger range of D and P. And that's all I want to talk about today. Thank you.
I'm wondering if the number of communication rounds have anything to do with...
So all of these are one round of communications, just a single message from Alice to Bob.
Right. So if we, allow for a couple of rounds...
So we have a slightly better scheme for set of sets that uses like 4 or 5 rounds. In particular, it is better if you don't know D. If you don't know D, the usual strategy is to take like log D rounds where you keep doubling D until it works. But we have a 5-round scheme that is a little more complicated that works there too. Other than reducing to a higher round scheme of set reconciliation, I don't know if we don't have other high round schemes for graph reconciliation.
Can you say anything about lower bounds?
Not really. I mean, there's a straightforward like D log U lower bound for set of sets, but our best upper bound is like D log U, so there is a gap there that I don't know how to close. For general graph reconciliation, we've proved a lower bound of D log N, and I guess this uses D log N for our best random graph scheme, so still a gap there, but I think that comes down to set of sets. Sure. Thanks.
We'll resume in half an hour.